Wanted to work through an example of matter waves, in particular the idea, the concept that's due to Louis de Broglie that particles like electrons and protons and neutrons have corresponding matter waves, have wavelengths associated with them. In this particular example, we're asked to think about a proton. We're asked to think about a proton that's traveling first at a speed that's 2.87 times 10 to the 4 meters per second, and then secondly at a speed of 2.08 times 10 to the 8 meters per second. So two very different speeds, and we're going to calculate the wavelengths of the matter waves associated with that proton. The key equation that we want is de Broglie's equation for matter waves. It's a relationship between the momentum of the particles, like an electron, proton, or neutron, and the corresponding wavelength of those particles. That equation was that the wavelength of the matter waves, lambda, is equal to Planck's constant, h, divided by the momentum of the particles. So let's go ahead and for these two different speeds, the slower speed on the left-hand side, 2.9 roughly times 10 to the 4 meters per second. I mean, it's a very fast everyday speed, but it's the slower of the two subatomic speeds here. The proton on the right here is traveling much faster at about 2 times 10 to the 8 meters per second. So we're going to get two wavelengths corresponding to the two momenta, which lead to two different wavelengths. Core equation. The matter wave wavelength lambda is the value of Planck's constant divided by the momentum of the particle. So the higher the momentum, the shorter the wavelength we're going to figure out. In the first case, we can fill in the momentum of our particle in terms of the speed of the particle or the proton, 2.87 times 10 to the 4 meters per second is the speed. We want the momentum, and so I've written here the classical equation for momentum, mv. And then we can just go ahead and fill in the values of h, m, and v. And so I've gone ahead and filled in the numbers here. Here's Planck's constant. I filled it in the units of joules seconds. That's handy when we're working with the mass of the proton in kilograms, the speed of the proton in meters per second. They're all SI units. So I filled in Planck's constant. I filled in the mass of the proton, 1.67 times 10 to the minus 27 kilograms. I filled in the speed of the proton, 2.87 times 10 to the 4 meters per second. In this calculation here, there's a lot of cancellation of the units. You could see all the cancellations of the units if we replace joules in terms of the units of length, time, and mass. You find out that the units of this quantity here come out to be, as they've got to be, the units of length. So here's the result I got. The number is 13.8. This is picometers, so this is 10 to the minus 12 of a meters. It was just a handy unit to write this wavelength in. So this is a wavelength that's much shorter than atomic scales, which is sort of 10 to the minus 9, 10 to the minus 10 of a meter. It's much bigger than nuclear scales, which are more like 10 to the minus 15, 10 to the minus 14 of a meter. So it's somewhere in between the sort of atomic and nuclear scales. Let's go ahead and do this second calculation for the higher speed proton. Again, we want the wavelength of these protons. The wavelength of these protons is given by the de Broglie relation for the matter waves. That is the Planck constant divided by the momentum of the protons. We're going to fill in the momentum in terms of the speed because we're given the speed and the mass of the protons. But we've got to be a little careful here. This speed, unlike the first speed, is of order of the speed of light. Speed of light is 3 times 10 to the 8 meters per second. This is 2 times 10 to the 8 meters per second. So this is roughly 2/3 of the speed of light. So it's 2/3 of the speed of light. This is a relativistic proton. This is not a classical non-relativistic proton. And because it's a classical relativistic proton, we got to use the relativistic expression for the momentum. So I'm going to use gamma mv rather than just mv. At low speeds, gamma is 1. And so this mv is perfectly fine here because the speed is low compared to the speed of light. But for speeds close to the speed of light, then we've got to use gamma mv, and gamma will not be close to 1. So I filled in the numbers here. Here's again Planck's constant. I'm filling it in the units of joules seconds because I'm working in SI units here for mass and time and length. I filled in the denominator the mass of the proton. I filled in the speed of the proton. I've got to multiply in the denominator by gamma. That's the Lorentz factor. Remember, the Lorentz factor is 1 over the square root of 1 minus v squared divided by c squared, or v over c and the whole thing squared. So I've got to divide by gamma. Well, gamma itself is 1 over something. So it's equivalent to multiplying by that something that gamma is 1 over. That something that gamma is 1 over is the square root of 1 minus the ratio of the speed of the proton to the speed of light squared. That's what this factor is in the square root here. This is 1 over gamma, 1 minus v over c squared. Now, when I wrote the v and the c, I didn't write the times 10 to the 8 meters per second of the proton. I didn't write the times 10 to the 8 meters per second for the light. I didn't write those just to save some space, and because they were common factors in this numerator and denominator here and just cancel out. So gamma is simply the square root of 1 minus 2.04 divided by 3 squared. So it's roughly 1 minus 2/3 squared. Anyway, we carry out this product here and divisions here. I got an answer that is 1.43 in femtometers. That's this FM here. A femtometer is a convenient unit here, is 10 to the minus 15 of a meter. And so this is a much smaller wavelength because it's a much higher speed, much higher momentum proton. This is a wavelength that is of the order of the scale of atomic nuclei. It is a much shorter wavelength than this other wavelength corresponding to the lower speed proton, which was somewhere between the scales of atoms and atomic nuclei. Anyway, that was an example of the Broglie waves for a proton. It was an example where we had to be a little bit careful about these speeds. If the speeds are non-relativistic, you can use the non-relativistic expression for momentum mv. But if the speeds are relativistic, you've got to use the relativistic expression for momentum. That's gamma mv, mv times the Lorentz factor. The de Broglie waves that we've talked about in this example, de Broglie waves were calculated in this example, were a sort of foundation of Bohr's model of the atom, Bohr's wave particle model of the atom. It was a blending, a combining of this wave-like property of, in the atom case, electrons, with the particle-like property of electrons orbiting the nucleus that gave Bohr the wave particle model that was able to explain, for example, the stability of atoms and, for example, the line spectra that were emitted by atoms.